So when the CPU executes multiple processes that the users might submit, right? So it could be different programs, and each program itself could generate multiple processes. Again, we'll understand what a process is in detail in the next chapter. Again, please remember that we are solely focused on multi-programming environments where preemption is allowed, right? So we are only talking about preemptive multi-programming systems right now, right? So in such an instance, there are two modes of execution, broadly speaking, right? There is something called as a user mode, and the second one is called as a kernel mode, right? There is something called as a kernel mode. Again, this word kernel is something that we will encounter a lot of times in operating system. Now, what is a kernel? So if this is the whole operating system code that I have, the operating system code has tons of pieces. There is one part that is central. So kernel basically in English basically means the core. Okay, kernel basically means the core of something, or the central thing, or the core, the most important aspect. So the kernel of an operating system is basically the core pieces of software which enable the whole operating system. Again, operating systems can be very, very complex pieces of software with hundreds of thousands of lines of code, often running into millions of lines of code. Kernel is that part of the operating system that actually controls everything, right? So that's where the word kernel is often used. So many times when people talk about operating system, what they're talking about is kernel, because kernel is what controls most of the important resources, manages resources and things like that, right? So now, as I was mentioning, there are two modes of execution. Given a process, it can either execute in user mode or kernel mode. In a nutshell, you can think of user mode as any user written program, right? Any user written program and submit it. So suppose you write some test.c program. Let's say you write a C program. You submit it, right? When you execute for example, you compile this, you compile it using GCC or any of the compilers, then you would get something like a.out. When you execute it, what happens? This code is submitted to the operating system. The operating system takes over this code, loads this code into memory and gives the control to the control unit in the CPU for it to execute this whole program. And of course, the operating system controls the whole execution of this program itself. Now, every user submitted and user given program runs in user mode. Again, so in a user mode, again, there are a couple of important aspects here. In a user mode, preemption is very much possible. Preemption, or in a user mode, the operating system can come in and say, hey, I want to take control away from you, right? I want to preempt you, or I want to forcefully remove the control of this process or program from some resource like CPU or memory, whatever it is, right? So preemption is possible if you're operating in user mode. On the other hand, kernel mode, right? Kernel mode is think of it like a supervisory thing, right? So most of the key operating system functionality itself runs in kernel mode, right? So kernel mode is always non-preemptive. Kernel mode is always non-preemptive, which means, again, the core functionality of the operating system itself runs in kernel mode. Okay, for example, if the operating system has to clean up some memory, okay, if the operating system has to load something, okay, so whatever the operating system does is always in non-preemptive mode, which means while we are in kernel mode, the process cannot be preempted and relieved of control of it will not be forced to give away control, because it's the operating system. When you're operating in kernel mode, it is the operating system's kernel code, literally a very, very important piece of software that the operating system is running, is actually executing, right? Very important. So typically in the kernel mode, you have key operating system functionality that often runs in kernel mode. I'll show you some examples in this video itself, right? So very importantly, when something cannot be preempted, right? If something is not preempted, if preemption is not possible, then such a piece of software or such a sequence of instructions are set to run in an atomic fashion. So it's called the atomic execution of instructions. What is an atomic execution? If you have, let's say, a program or a process with a bunch of instructions, if this cannot be preempted from the very beginning to the end, everything has to finish. Even if the operating system cannot relinquish or cannot force it to give away control. okay, then we say that this is executed atomically, which means everything gets executed as if it's just one atom of instructions, or one logical set of instructions wherein you cannot preempt, right? So whenever there is a sequence of instructions that cannot be preempted, such a thing is said to be atomic. Such a thing is said to be executing atomically. So kernel mode, whenever you're in kernel mode, you always execute in atomic fashion because that code cannot be preempted. In the user mode, you can preempt left and right? So now let's see how the operating system itself does this. So for every program or process, okay, typically for a process, there is a data structure that the operating system maintains called the process status word, which is often written as PSW in short. Suppose, imagine if I'm creating a new process. Okay, let's assume this is my process 1. It has a bunch of instructions that I have to execute. Along with it, for this process, it creates a PSW corresponding to this process. Okay, and within the PSW, there is one bit, there is one binary bit literally, which is called the mode bit, right? Again, since we have only two modes, look at this. We have a user mode and we have a kernel mode, right? So this is a special data structure. This is a special data structure. And what data structure is it? It is just a bunch of bits. So for every process associated with every process, there is a special data structure called the PSW, the process status word, right? Again, the instructions of the process themselves are here, but corresponding to this, I have some metadata. I have some additional data about the process itself that I store, right? Now there is a bit here called the mode bit. This mode bit can either be 0 or 1 because it's a bit, right? Typically, if the mode bit is set to 0, then this process is set to be running in user mode. If this bit is set to 1, this process is set to be running in kernel mode. Remember, given a single process, a process can start in user mode, can go to kernel mode, can come back to user mode, go to kernel mode. It can keep jumping from one mode to other mode, right? So, but remember that if the process is running in kernel mode, which implies no preemption is possible, right? If it's in user mode, yes. If it's in user mode, the operating system can say, sorry, please wait for some other important process that I have to run right now, right? So this bit called the mode bit in a special data structure called as a process status word. Again, most operating systems, for every process, they maintain this special data structure called process status word, where it stores lots of things. Okay, where it stores lots of things. One of the things that it stores is called the mode bit, which helps us determine at any point if the process is running in user mode or kernel mode, right? Very simple concept here. Now, of course, given a program or given a process, it can run in user mode or kernel mode. Again, right now I'm using the words process and program interchangeably. But there are some differences between them that we will discuss in the next chapter. Okay. Again, process is what we care about mostly in operating systems. Again, we will dive into what a process is. How is it different from a program? How can one program generate multiple processes? We will learn about all of them little later. Okay, in the next chapter in lots of detail. Okay, now let's look at some simple code. Again, this code works on Unix. Okay, remember that in the operating system course, we will focus a lot on Unix based operating systems like Unix, Linux, Mac, Android, right? So these are all Unix based operating systems. There are many other Unix based operating systems like BSD Linux, etc. Right? But most of the code that we learn, because Unix was the original multi-programming preemptive operating system, which is the basis for all of them. If you notice, we don't focus too much on Windows. Of course, while Windows is one of the most popular operating systems out there, the best platform or the best operating system to learn operating systems itself are Unix based operating systems. Okay. So imagine if I write a code like this. Okay. Here, there is an include that we need to include. So there is something called #include unistd.h. Okay. So this has a bunch of functionality, okay, which I'll talk about later. Again, this type of code works if you have a Linux box or a Mac. You can even make this work on Android. This code may not work on Windows. Please understand that. Okay. Unless you have some special software, which will simulate Unix based system on Windows. Okay, so let me explain this code here. Okay, we include this because we have a function called fork here. The definition of the fork function is actually there in this header file. Okay, or the declaration, to be precise, the declaration of the fork is here. The definition itself, it's in some library files. Okay, so let's go step by step here. What are we doing? We're declaring 3 variables here, which means in the memory what happens? Which means in the memory I'll have some place to store A, some place to store B, some place to store C. Now I'm saying C equals to A plus B. There are some random values here. These values will be added and stored into C. Here comes a function that you may not have studied till now. This is called the fork function. So what it does is very, very interesting. Look at this. What it does is very, very interesting. This is again till now, while these 2 lines are being executed, the program executes in user mode. The program is again, for each of these lines, you'll have a bunch of instructions. This line will translate to a bunch of machine level instructions. This line will translate into a bunch of machine level instructions. While these instructions are being run, this program, remember, this program itself has a PSW associated with it. Let's assume this is a PSW associated, the process status word associated that we've just discussed of this process, right? So this process itself has your mode bit, This is initially 0 because we are in the user mode, because this is a user written program. But the moment you call this function called fork, this is where things start becoming very interesting. What this fork does is, this fork is often called as the system call. This fork is often called as a system call, or in short syscall. Okay, so this fork is calling a function. Again, this function itself is this function declaration itself is in unistd.h, but this function eventually calls the operating system. The operating system has a bunch of functions. Look at this. The operating system has a bunch of functions which it can call. What fork does, very, very interestingly, is fork creates a new process. Okay, so let me explain this. So let's assume this whole thing is running as process 1. Okay, this whole thing is running as process 1, right? So where am I right now? I've executed this line. So let's write line 1, line 2, line 3, line 4. Okay, I've executed line 1, I've executed line 2. I'm executing line 3 now. In line 3, I said fork. This fork is a system call. It's an operating system call, literally. So what it does is, it gives the control to the operating system. Within the operating system, there is functionality which tells what to do when fork is called. What fork does is, it creates a new process. Look at this, very interestingly. Fork creates a new process. It copies this whole process now. Whatever is there in this process, look at this, whatever source code, whatever instructions are there in this process, it simply copies them. Very interestingly, right? Whatever variables are there, it also copies them. Of course, the variables correspond. See, look at this. Here I have ABC. This ABC will be stored in some memory location. This again creates other values for ABC. This ABC corresponding to process 1 are different from this ABC corresponding to process 2. So fork basically means fork a new process, or spawn a new process, or create a new process, wherein you copy all these instructions here. And now what happens is, this process will not run all the instructions. Again, let's say we have 4 lines here, right? Line 1, line 2, line 3, line 4. When we're executing line 3, so this is line 1, this is line 2, this is line 3, this is line 4, right? So this is executed, this is executed. While executing fork, what did the operating system do? The operating system took the control, which means now we went from user mode to kernel mode, right? The operating system took the whole control. So it goes into kernel mode now. When it goes into kernel mode, what the operating system does is, it takes all the instructions, all the memory that is associated with it, it creates a copy of that. Very interestingly, right? So this is what the fork function, when it calls a system call or an OS API, right? Just think of it like a system call. It's a function call, but it's a function call to some function in the operating system kernel itself. So it goes into kernel mode. Within the kernel mode, it creates this new process. Now what does it do very interestingly? Now it transfers the control to whatever is there after the fork line. So this process 2 will start executing from line 4 now. This is line 1, line 2, line 3, line 4, right? So process 2 does not execute from the starting. It starts executing from the line after the fork, which means it starts executing from the 4th line, right? Now this whole process will finish executing. Once it finishes executing, the control goes back to process 1. Look at this. So we are starting in process 1. This is executed. This is executed. The moment I call, so both of them are in user mode. I called fork. The moment I call fork, I go into kernel mode. And now I create a new process where I copy all of these process instructions. I copy the memory locations into different memory locations. So the ABC here are different from ABC here. Right? I'll show you more examples for you to understand this better. Right? Now this process 2 will start executing from the line after the fork line, which means it will execute the printf. Right? It executes the printf. Now, once it finishes the program, look at this. Once it finishes the program, the control comes back to the line after the fork here. So this is called the parent process. This is called the parent process, and this is called the child process. Why is it called the parent process? Because this process created this process. Right? So this is called the child process, and this is called the parent process. Now, how does this whole program work? What output does it generate? Look at this. In my parent process, I execute 1, 2, I called fork. So the control goes to my child process. In the child process, I'll print high. Right? In the child process, I print high. Right? This is my print high, the fourth line. Then, after that, in the child process, there are no more lines. So I go to the fourth line. So my control goes to the fourth line in parent process. In the parent process, again, I have high. So I'll print high. So what does this result in? This results in printing high twice. Again, fork is a very, very important call, very, very important system call, which creates new processes, right? So what is happening here? The same, whatever is there in the parent is being copied exactly into the child process. Again, we'll see more complex examples. Fork is one of the most powerful. Again, I have personally used fork to create fairly complex multi-threaded programs, especially for scientific computing and for machine learning. So fork is super duper powerful concept. Now you might wonder, okay, fork exists in Linux, Mac, Android. What about Windows? So in Windows, again, I'm not a Windows expert. I'm not a Windows operating system expert because I've not used it extensively. In Windows, there is a function called spawn, right? Which does similar work to what fork does in Unix. Again, Windows itself is not Unix compliant. While Windows, some of the core concepts of Windows are inspired from Unix, Windows itself has their own functions, own naming, everything of its own, right? So if you know Linux, you can use Mac very easily. Why do most developers want to use a Mac? Because it's very similar to a Unix or Linux system at its very core, right? So there is a function called spawn and related functions called spawn on Windows, which perform the same or similar task to what fork does on a Unix based system, right? Very simple. Okay. Now let's look at slightly more interesting example. What if we have a function like this? Look at this. We have two forks here. Okay. So let's talk about the first. Look at this. This is my first program. Okay. So I'll write this in short form. Again, I have added this header file. So I have a fork. I'll just write fork as F. Okay. Just for short. I have a fork here. Then I have a printf. Okay. This is my program. I'm executing this. The first line itself is fork. When we say fork, what happens? It creates a new process. Look at this. This creates a new process now. This creates a new process. So it creates a new process now. Let's call this process as P2. Okay. In this P2, the same code is copied or the same instructions are copied. But where does this start running from? Look at this. This starts running from this line. What did we discuss a while ago? In the child process starts executing from the line after the fork line. Right? So here again, there's one more important thing that I forgot to mention. So here in these two things, we are in the user mode. When the fork was called, we went into kernel mode, created the child process. Then when we start printing this is again in user mode. Okay. This example was created to help you understand how we can change from user mode to kernel mode and kernel mode to user mode. We often go into kernel mode when we have some system calls like this, which are performed or which are executed by the operating system itself. Okay, let's look at slightly more interest. Fork is a beautiful thing. Okay, so I have this program. I started with fork. The moment I say fork, what happens? We go into kernel mode, right? The operating system creates a new process here. And where does it move the control? It moves the control to the next line. So again, it calls a fork. So what happens now? It creates a new process, right? Let's call this process 3. Again, this has 3 lines: fork, printf. Where does the control go? The control goes here now, right? Because again, this is parent, this is child, this is the child of this. Okay, this is its parent, this is its parent. Now this printf, right? So what happens now? We printf high. Okay, let's write whatever is the printf, let's write it here. This is done. Look at this. Once this is done, what happens? The control goes back to this line now. See, this is executed, the control goes back here. Now here again I printf. When I printf, what happens? I get high. Very good. Now once this is over, where does the control go? The control goes back here. Now here again it will fork. Look at this. This again forks. Now which means I create process 4. In process 4, what happens? I have fork printf. Because this is line 2, my control goes to line 3 now. Right? Line 3, what is there? There is printf. So I'll again print high. After this, where does the control go back to? The control goes back to this. Now what do? I again printf high. So I have 4 highs. Let me number them, right? So this is my first. I go here, right? My control goes here. This is the second step. This executes. This is the third step back. After this, I go here, 4th step. From here, I go here, 5th step. This is executed, 6th step. Then I end everything. Look at this. Here I have 2 forks. And how many total processes got created? 2 power 2 processes got created. 2 power 2 process, including the original process. This is the parent of all of these processes, right? So similarly, if you have a program, let's say with n forks. Okay, if you have n forks in a given program, right? Here we have 2 forks and we created 2 power 2 processes. Here what do we have? Here we have only 1 fork and we created 2 power 1 processes. If you have n forks, we will create 2 power n processes, including the first parent process. Okay, very simple example. Again, if you understand how fork works, it's a very, very simple thing to grasp this concept, right? Now let's go into a slightly more tricky thing. This is very interesting. Now this fork function also returns something. What does it return? Look at this. The fork function in Unix or in Linux or in Mac or even on Android, the fork function returns the ID of, okay, let me explain this, right? Let me explain this with an example. I think this will make it fun. Okay, so let's say this is my parent process, right? And this is my child process which is created. So I start here. I have an ID associated with it. Look at this. I have an ID here. So this process has a variable called ID in the memory. Okay. So I'm saying ID equals to fork. I'm saying ID equals to fork. So this is in user mode. It goes into kernel mode now. The moment I say fork, what happens? This whole program is copied here. The whole program is copied here. Variable ID is also here. But what happens here is ID is equal to whatever the fork returns. What does the fork return? The fork for the parent process. Again, this is my parent process. Remember that this is my parent process. This is my child process. In the parent process, this ID will point to every process has something called as a process ID. Okay, let me show you process IDs so that you appreciate this concept better, right? So every process has a process ID. Look at this. Okay, so threads. Okay, look at this. Look at this here. Okay, so there is this thing called PID. Again, I am on a Mac, right? These are all the processes. This is the CPU time, threads, all of that stuff. Look at this column here, PID. What does this PID mean? PID means process ID. Look at this. PID means process ID. So what happens is for every process, there is a ID that is given, which is a positive number. Okay, let's assume this process ID is 1211. Every process has a process ID. Let's assume the process ID is 1011. So what fork does is, fork returns the process ID of the child here. So what happens to the ID here? In the parent process. Remember, this is the parent process. This is the variable ID in the parent process. This is the variable ID corresponding to the child process. These are your instructions. This is your memory. These are your instructions. This is the memory corresponding to it. So this ID will be equal to 1211. What is 1211? 1211 is the PID or the process ID of the child. And process IDs, again, remember that this is your process ID. Process IDs are always greater than 0. While in the child, what happens to the ID? Look at this. What happens to the ID in the child? The ID in the child is equal to 0. Very important. Okay. The ID, what did we do? We wrote ID equals to fork. So fork returns to the parent process. The fork returns the ID of the child process created. Again, think of it like a unique identifier. Every process is identified using this ID. Okay, we'll see how PIDs are created, all of that when we go into process management itself. Okay, but just remember that just like we have roll numbers, every process has, just like students have roll numbers or some identification numbers, every process has an ID. Okay, the child process, again, this variable ID, the child process has an ID of 1211, which is given, which is returned to which is returned to the parent. So the ID variable in the parent has the PID of the child. The ID variable here in the child itself has 0. So now I can write code like this. If ID equals to 0, if I want my child process to execute these lines of code, okay, so only these lines of code will be executed by my child process. Okay, while if ID is greater than 0, which means this is in the parent process. So your parent process will only execute these lines of code. Your child process will only execute these lines of code. So using the return type of ID, I can determine what lines will be executed by the parent, what lines will be executed by the child. Now imagine if your ID is negative. What does that mean? If your fork returns a negative value, look at this, I've written an else condition also. It means the operating system could not fork a new process. That could be because you don't have memory, there is some issue. Okay, so this function called p-error, which is available on Unix based system, is like a printf. Okay, it's like a printf which prints errors. Okay, this basically means process errors. Okay, it says I have an error which is unable to fork. So the fork function itself returns numbers, returns integers to be precise. If it returns 0, that means you are in the child process. If it returns a non-zero positive number, right, it means you are in the parent process. If it returns a negative number, you have some error that occurred. Very important. Remember, the ID in the parent is different from the ID in the child. Very, very important aspect of fork. Okay. Now let's look at a simple, nice example. Very nice example. Okay. Slightly tricky, but if you get it, it's very, very good. Now look at this. Int ID A10. ID equals to fork. Okay. So what happens now? I have one process here, parent process. I have another process, child process. Okay. Very good. So this parent process obviously has an ID and A. There are two numbers here. Very simple. There is a value A here. There is a value ID here. The child also will have A and ID. In both these cases, A equals to 10. Right. So this case, A equals to 10. Right. A equals to 10. Even in this case, A equals to 10. What happens to the ID? This ID here, in this case, the ID is greater than 0. In this case, the ID will be equal to 0 because this is a parent process. This is the child process. Right. If ID equals to 0, what are we doing? See, in this case, in this program, when this program is being executed, my ID equals to 0. So the child process will execute this. So what does the child process do? It says A equals to A plus 5. And what are we printing? We are printing A and address of A. Okay. So what does the child process print? What does the child process print? The child process prints the value of A. What is A? A was initially 10. So we made A equals to A plus 5. So this A becomes 15. So the child will print 15 and the address of A. Cool. Very good. Okay. Now, of course, the parent process will not execute this because in the parent process case, this ID is greater than 0. But the parent process will execute these lines. So what is the parent? Again, the child process executes these lines because ID equals to 0 in the child. The parent process will execute these two lines. What does the parent process execute? Okay, let's see what the parent process outputs. The parent process outputs A equals to A minus 5, which means in the case of parent process, A becomes 5. It says print A and address of A. Print A. What is A now? A equals to 5. And the address of A. Remember that these two addresses are different because this address corresponds to A, which is part of process 1. This A is different from this A. This is completely different address location. So these two addresses, these two values are not the same. Right? The variable names are the same, but they're two different addresses altogether. Now the question here is, if U and V are the values printed by the parent. So this is U, this is V. And if X and Y are values printed by the child, then which of these four conditions is true? Look at this. V and Y cannot be the same because this is the address of A in the parent process. Right? This is the address of A in the child process. Remember that the parent process has a variable A that it operates on. The child process has a variable A that it operates on. When the child process was created, the value was copied, but then they both become independent to each other. So V is not equal to Y, which means this cannot be the answer. This cannot be the answer. Okay, either A or D can be answers. Now let's look at this. What about U and X? Right, look at this. So U are printed by the parent, right? Sorry, I need to change this. Okay, U and V are printed by the parent. Sorry. So parent prints U and V. Parent prints U and V. The child prints X and Y. Right? So now what does it say? U plus 10, 5 plus 10 equals to X. X. This condition is true. This condition is not true. right? Look at this. My parent is printing 5, my child is printing X, right? My parent is printing 5 and my child is printing 15. That's what it says. So U plus 10 equals to X. So option D is the right option. Again, to answer such a question, all you need to understand is how fork works, what is the return type of fork, and the fact that when we fork, the values of the values in the variable are copied, but each process has an independent set of same variables, right? Very, very interesting problem to understand how fork works. And again, this whole topic of fork, we started off to explain you about the user mode and kernel mode. So when the fork function itself is being executed, we are in kernel mode. But once we create the child process, once we are back to either in the child process or in the parent process, when we are outside the fork function itself, we go back to user mode. So a program can jump from user mode to kernel mode and back. It can keep jumping, and it keeps track of that by using the mode bit in the PSW.